Electricity may seem like you need a quantum mechanics degree to understand it, but in this guide, you're going to learn about the basics of electricity and also about how to make basic circuits for your DIY projects. This would lead into the next video, which is about taking the circuit design and implementing it on a PCB design and fabricating it using a PCB manufacturer like PCBWay. The sponsor of this video, but more on them later. Alright, so let's talk about electricity by talking about water, because it's a very good analogy for electricity. So we have this reservoir of water, and at the end of it is a water pump. This pump can take the water and pressurize it, making the water flow through the pipe. More pressure, which you can think of as a pushing force, means a higher flow rate of the water. At a certain spot in the pipe, there is a kink. Before this kink, we have full water pressure, which is the pressure created by the pump. But after the kink, there is less pressure in the water. Think of how a kinked garden hose would only let out a weak, lower pressure stream of water compared to if there wasn't a kink. If the kink was tighter, we'd have less flow rate. Thing is, the flow rate of water going into that pipe is the same flow rate of water going out of it. This makes sense because if 5 gallons per second of water go in, but 1 gallon per second of water comes out, then what happened to the other 4 gallons per second? Water can't simply disappear like that. So flow rate into and out of a hose is the same. If we replace the kink with a water mill or a turbine, we can do some useful things with that flow of water. Now, analogies aren't a one-to-one representation of the real thing, but they can be pretty close. So let's see how this analogy relates to electric circuits. A battery, or a power source, is like the water pump. The battery provides a voltage, which is like the pressure from the water pump, and this voltage can push electrons through wires, which is like the water pipe, causing a flow rate of electrons called electric current. Resistors can impede the flow of electrons, similar to how a kink in the pipe can impede the flow of water. Resistors also create a voltage drop, meaning the voltage before the resistor is higher than after the resistor, similar to the pressure drop in the water analogy. The flow rate of electrons, or current, throughout a single path is determined by how much voltage and resistance there is, and is the same throughout the single path. Similar to the water analogy, if you increase voltage, you increase the electric current, which is the flow rate of electrons. If you increase the resistance of the resistor, you decrease the electric current. This is called Ohm's law. Ohm's law states that current in units of amps in a series circuit equals voltage in volts divided by resistance in ohms, hence the name. If you multiply the voltage drop of a component with the current going through it, then you get the power that goes through that component. A series circuit, or path, is one that has only one possible path between the higher voltage or positive side of the battery to a lower voltage. This is opposed to a parallel circuit, which has multiple paths. Now we usually think of electricity as the flow of positive charges and not negative charges like electrons. In reality, the electrons are what flow through wires, but I think this perspective of positive charges flowing comes from Ben Franklin thinking positive charges are the ones that flow, and we just stuck to it, and we call that conventional flow. Thinking of electricity as the flow of electrons is called electron flow. Both are valid and will work in electronics, but the symbols and methods are in reference to how the flow of positive charges flow, from positive to negative. So we'll just stick to that. Okay, so let's see some circuit examples. For that, we'll be using Tinkercad to show some of the basic circuit concepts. You can follow along by making an account and going to the Circuits tab, or you can just follow along for now. I highly recommend experimenting with different things here. It's free, and it'll help you learn the basics. Alright, so here we have a circuit, and in Tinkercad you can go to the Circuits tab and essentially drag in objects, and then connect them, and then you can use wires to connect more stuff together. So that's basically how I created the circuit. I'm not going to show you that right now. It's just basic dragging and clicking and pressing things together. So we're going to start the simulation here. And this here is a power supply. So it basically creates a voltage, and then you can adjust how much current can come out of it. But for now, we're just going to set it to the max, the maximum possible current. So we have 9 volts. And if we were to take these resistors here and take a look at the resistances, 2 ohms, 5 ohms, and 2 ohms, you'll notice that Ohm's law is current, I, which is here, equaling the voltage divided by the resistance. Now, what is that resistance? Well, if you have resistors one after the other in series, then the resistances just add together, which makes sense. So let's add these together. So 2, 5, and 2, that makes 9 ohms. So then we would have current equaling 9 volts divided by the 9 ohms, which is 1 amp or 1,000 milliamps. That's another way of writing 1 amp. So that's basically Ohm's law. So it makes sense. If you have more resistance, let's say let's just make this one 100, then you would have less amperage, less current. And by the way, this is called a multimeter, and you can use it to measure multiple things like resistance or voltage. So in real life, you would have a tool called a multimeter as well, but it looks a bit different. So here I can measure voltage across this resistor. There's a 4.46 volt drop across this resistor. The resistance of this is 100 ohms. Now, the next thing is, what usage do resistors have? Well, there are many usages, but one of them is to reduce the current so that a component wouldn't blow up. Here we have a resistor with 2 ohms. Okay, 9 volts, 2 ohms. That's a lot of current. But as you can see here, it blows up, and it says that there are 159 milliamps going through. Current rating of that LED is 20 milliamps. So obviously we exceeded that rating. So generally a good value is in the hundreds of ohms, and that should be fine. That's a bit close, so maybe 500. And now it goes pretty normally, 14 milliamps. And of course, if we have, for some reason, more voltage, then we would need more resistance again, so that the same amount of current can go through. So that's one usage of resistors. There's also other ways of using resistors, like voltage dividers, to feed a specific voltage through to another component for like data or for a voltage comparison and stuff like that. But that's probably for another video or another topic. Everything that we've seen before has only one path. But here, don't get too flustered with all of this here. There are multiple ways for positive charges to go from positive to negative. So it can take this loop or this path right here. It can also take the middle path, as we'll call it, and then it can take the very rightmost path. So let's fire this thing up and see what happens. There will be some things that we'll notice here. This current is the current going through this path right here, and then this current through that path, this current through that path. Notice what this number is. You'll notice that if we add 100 milliamps with 60 milliamps and 75 milliamps, you'll get 235 milliamps. And over here, you'll notice that 7.5 volts, the voltage drop across this resistor, and 22.5 volts will equal, if I could do math, 30 volts, which is that number up there. What you just saw there is Kirchhoff's voltage and current laws. Kirchhoff's voltage law states that the voltage drops in a path loop add up to 0. Kirchhoff's current law states that the currents going into a junction need to equal the currents going out of it. Makes sense if you think of water, where you can't have more water coming out of something than coming in, or vice versa. Now that you know the basics of electric circuits, you'll want to know how to do stuff with it. So the first thing that we'll talk about is the microcontroller. Microcontrollers are things that you can program, meaning you can type up instructions on your computer, upload the instructions to that microcontroller, and have it control other things using electricity in the way that you instructed it to. Think of it as the brain of your electronics project. There are different metal pins on a microcontroller, some of which can be used as inputs or outputs of voltages to receive and send information respectively. Other pins are more basic, things like power input and ground, which is where you would connect the negative side of a power supply, like a 9-volt battery. Now, if you were to try and use this microcontroller chip on its own, you'd be stuck with needing to design a whole circuit board to make it work and to allow you to upload programs to it. Fortunately, companies like Arduino have already done the circuit board design with the microcontroller on it. There's a lot going on this Arduino Uno, but the main focus is the pins on the edges. This right here, VN and ground, allow you to power the microcontroller by connecting VN to the positive side of a power source and ground to the negative side. You can also power it with a USB cord or a barrel jack. The 5 volt and 3.3 volt pins allow you to get a voltage from this board. So you can power other things from this board. Obviously, the board would have to be powered by something else in the first place. The rest of the Arduino's pins are mainly used to input or output a signal. These here are digital I/O pins, short for digital input or output. Digital means that we can only output or input 5 volts or 0 volts. And then you can program them to output a digital signal to actually do something, like turn a motor. Over here, we have the analog pins. These can only take in an analog signal, which is a signal that can vary in voltage. So it doesn't have to be only 5 volts or 0 volts. These can come in handy for many different sensors that need it. All right, so we have these microcontrollers and they can control stuff, but what are these sensors that they control? Sensors can sense many things, depending on the sensor. For example, distance sensors can measure distance, and IMUs can measure acceleration and rotation. You can think of sensors as your human senses, like sight, feel, or touch. In general, we connect these sensors to digital or analog pins, some of which can tell the sensor to activate and get measurements, while other pins are used to get the measurements to the Arduino so that we can do some interesting stuff with it. Take an ultrasonic sensor, for example. For this specific one, we can use an Arduino's digital pin to send a voltage signal to the sensor's trigger pin, causing the sensor to emit ultrasonic waves. Right when it does that, the echo pin turns on, sending a voltage back to a separate digital pin, and when the ultrasonic wave returns to the sensor at its receiver, it turns off the echo pin. The time between the echo pin turning on and off is how long it took for the wave to make a round trip. And we can use that to calculate the distance with a basic formula with speed and time. Now, how the sensor works and how to use it is explained in something called a data sheet, which in general can explain its characteristics and how to use any electronic component. Before we move on, I want to talk about PCBWay, the sponsor of today's video. Electronic circuits can work on their own when put together with wired connections. However, it is only good for when you are prototyping, not for a polished, reliable, finished design. So that's where PCBWay comes in. With PCBWay, you can implement your electronic design onto a PCB design by sending them your PCB design files. Once you define your parameters for the PCB, you can get your PCB within about a week's time, and then you can solder your components onto it to have a finished product. This process of sending in your PCB design, the PCB design itself, and getting the fabricated PCB will be covered in the next video. PCBWay can also manufacture non-PCB related designs, such as mechanical designs with their 3D printing services and metal manufacturing services. All right, back to the video. So the Arduino can know what's going on around it with sensors. Now we want to do stuff with that information. If we want to move around in response to that information, we can use actuators. Actuators are things that can cause movement, like motors and pistons. They can connect to some wheels to make a robot move forward, or to an arm to move something else. There are multiple types of motors, like brushed DC motors, brushless DC motors, stepper motors, and many more. However, the main concept of being able to move stuff with them, especially after getting information from a sensor, still applies. And that leaves us with the other stuff in electronics. Things like LEDs, MOSFETs, H-bridge chips, and capacitors. Some of these help to make the microcontrollers, actuators, or sensors work better, or just outright work. For example, in between an Arduino and a motor, there would have to be a MOSFET or an H-bridge driver as an intermediary. This is because the Arduino can't provide enough current through its pins. That's just the surface level explanation of how the extra components work, but the point is that they are able to make the main components work. There are many components which I can't cover in one general video.
All right, so we know a little bit about basic circuits and also about the different electronic components. So now let's get back into Tinkercad and see how it all comes together, with the first circuit being an Arduino, an ultrasonic distance sensor, and an LED.
Okay, we've graduated from basic circuits to all of this, which might seem like a very big leap, but let's just see what this thing does. We have this sensor, the HC-SR04, and it's an ultrasonic sensor. In the simulation, this represents like an object that is a distance away from it, and we can drag that object, that simulated object, away. So just notice what happens to this LED. As the object gets farther away, the LED gets brighter. When it's close, right here, it's dim. Here we have a recognizable like LED with a resistor in front of it. And as we saw before, that resistor is meant to reduce the current going through this resistor so that it doesn't blow it up. And then this wire here just goes to the opposite end of the power supply. So you can think of this as the negative side of a battery, the ground, and then this side as the positive. And as you've seen before in the microcontroller animations, we can output a voltage or a signal from these pins over here, and that can create a current. The other things for this circuit would be this ultrasonic sensor. So let's break this down. VCC, indicated by the red wire that's connected to it, indicates where you would input the positive side of the battery or power supply. So this is how you would power this ultrasonic sensor. And then ground is how you would have the positive charges go through this and out to the negative side of the battery or the negative side of this board's power supply. Now, what are trig and echo? Well, you've seen in the animations, the moment that you turn this trigger pin on, the echo pin turns on, and then when the signal comes back, it turns off. And that's how you would be able to time how long the wave was traveling for. And so you'd sort of be able to see that here, where I'm going to go over this code in another video pretty in depth and how you would program an Arduino. Okay, so we basically took our LED circuit and we've replaced the LED with a motor circuit, which looks very complicated. But if we demystify it, it's actually pretty simple. So let's just see what this actually does. And it's a very similar concept, except now with a motor. So we can see it's going at like 2000 RPM. If we increase the distance, then, well, we increase the current. So now it's spinning at 13,000 RPM. Well, the ultrasonic side is the exact same as before. Over here is where things get interesting. We have this chip right here, and then we have this motor, and then we have this power supply. So how does this all play together? Well, let's talk about the Arduino. The Arduino can only provide a weak 5-volt signal that can only create around 20 milliamps. If we were to try and just connect this output, digital output, and this digital output to the pins of this motor, for example, it will blow up. So what do? We take those weak signals and we feed it through this thing. And how in the world would this thing be able to power this? Well, this chip right here doesn't just magically turn a weak 5-volt signal into a powerful higher voltage signal, for example, with more current. It does that by taking voltage and current from a power supply, for example, that can provide a large amount of current. So we essentially take that, right? And it goes into power 2, which is a pin that is designed to take in a higher voltage. And then we just have the ground pins, which, like the ultrasonic sensor with the ground pin, would just be connected to the negative side of the power supply. Okay, we have power 1. So what's that? What's the difference between power 1 and power 2? Power 1 just connects to, let's see here, this is a breadboard, so we can see how everything's connected together. That would connect to 5 volts of the Arduino. So it takes a lower voltage, but it's only needed for turning this thing on so that it can work, quote unquote. And then obviously this chip right here is connected to this motor. And then the other side of that motor is connected to, again, this chip. So how does this actually turn on? If we program this pin and turn it on to 5 volts, it'll go into input 3, which means the output 3 would also turn on, but it won't turn on with 5 volts. It'll turn on with 9 volts. So we got 9 volts here. And more importantly, we will have 9 volts and as much current as we want from it, ideally. So if we have 9 volts here by sending a 5-volt signal to input 3, then what would we need for output 4? So what we do is we send 0 volts from this pin. So that input 4 gets 0 volts and output 4 also gets 0 volts. So you have 0 volts here and 9 volts here, and then you have the motor spinning. And that's basically what this chip does. It takes a lower voltage from an Arduino, a weaker lower voltage from an Arduino with less current capability, and it turns it into a higher voltage with a lot more current capability so that it can drive a motor. That's why it's called a motor driver. Now there's this one last pin right here, enable 3 and 4, which, as you might guess, is used to enable inputs, outputs 3 and 4. And to enable it, you would just connect it to 5 volts. Of course, you can make the Tinkercad circuit in real life with a breadboard, but you can imagine if the circuit was bigger, you could see how messy it gets. The solution? Printed circuit boards, PCBs for short. PCBs are essentially metal boards that can make the same electrical connections between components, but do it more compactly and securely compared to using normal wires. This is because the wires are embedded in the board, and the connections to the board are made through melting metal, which is much more permanent than a friction fit in a breadboard hole, for example. If you want to know how to design one, well, the next video of the series is about PCB design. In general, I will release the next videos of the series every few days or so keep an eye out. If you want to learn how to do PCB design, click on the video shown on the screen once it releases.